Hello everyone, I'm Jaydeep Saha, representing the Electrical Machines and Drives Lab at National University of Singapore, and today I'm going to present our work on the modulation of direct matrix-based dual-active bridge AC-DC converters. I'd introduce the topic, give an outline of the topologies and modulation, provide a brief on the analysis of modulation boundaries, show the simulation and experimental results, and then give a objective conclusion. Solid-state transformers are nothing but isolated multi-level converters, as you can see in the diagram on the right, which is essentially a medium voltage AC to low voltage DC solid-state transformer. And it has been shown in literature that such solid-state transformers are economically justifiable if a medium voltage AC to low voltage DC conversion is involved. As you can see in the each cell of this SST, which is a single stage AC-DC conversion stage connected in an ISOP configuration, that is input series output parallel configuration. There is a front-end AC to MFAC functional block followed by a medium frequency transfer and then a medium frequency AC to DC function block. For the AC MFAC conversion, we have two options, that is the AC to DC plus DC to AC two-stage conversion strategy with intermediate DC link, and the AC to MFAC direct conversion strategy, which is a single stage one. It is also known as the front-end matrix-based single-stage single-phase AC-DC conversion strategy, which has been observed to offer better efficiency and power density. The suitable front-edge matrix-based single-stage single-phase AC-DC converters are judged in the literature on the basis of the criteria of efficiency, power density, cost, failure rate, control complexity, etc. And the two suitable configurations obtained are the front-end half-bridge matrix-based dual-active bridge and the front-end full-bridge matrix-based dual-active bridge, which are referred as FEHB and FEFB-MBDAB in this entire presentation. However, the exhaustive set of modulation modes for these two configurations are not studied in the literature, and thus the modulation constraints are still unclear or unknown. So looking at the front-end half-bridge MBDAB, we can see that there is a front-end half-bridge matrix converter at the front end, which can generate a two-level waveform, that is the primary voltage VP, and on the secondary side we have a conventional H bridge which can generate a three-level waveform with controllable pulse width and phase shift. So we can see the modulation modes, that is the three possible modulation modes for both ZCS constraint and ZVS constraint modulation. So ZCS constraint means that when VP changes its level from plus VAC by 2 to minus VAC by 2, the current should be 0. Whereas for ZVS constraint modulation modes, the current at the level change of VP should be enough to facilitate the ZVS transition. And also, as you can see, typical of the half bridge, there is a step down of 0.5 when it goes from VAC to VP. Now coming to the full bridge configuration, we can see that there is a front-end full bridge matrix converter, thus there is no step down of 0.5. However, both VP and VS are three-level waveforms with controllable pulse width and phase shift. So apart from the three modulation modes described earlier, which continues to apply in this configuration as well, with a slight change that VP now becomes equals to VAC, as there is no step down facility here. In addition to that, as there is more control flexibility, we have four more modes of modulation, that is 4 to 7, both in the ZCS constraint and ZVS constraint types. Also, the power transfer equations and their maximum and minimum limits for all the 7 modes are being discussed in the paper, and I'll not discuss here for the sake of brevity. I'll straight away go to the analysis of the modulation boundaries, where each of these curves show the minimum and maximum power transfer in each of the modes. So if you look at the switching cycles average power transfer versus the NVAC by VDC, this true ratio of voltages. Uh, so we can see the modulation boundaries in this reference frame for the front-end hub bridge configuration. You can see each of these dotted lines basically show the locus of operation when the VAC peak by VDC, this ratio is different. So let's say when the NVAC peak by VDC is 0.688, so when the power is being transferred from zero to peak of AC cycle and back to zero, the sinusoidal power transfer, we can think of it as it is going from zero to peak and coming back. So that is how the locus thing works. So for the ratio of 0.688, we can see there's a transition between two modes, that is mode 1 and mode 2. For ratio of 1.18, it's restricted to just mode 1, and for ratio of 2, it predominantly is in mode 1, and there's a portion where none of the modes are able to transfer the power, required power. So these ramifications are shown in the scapt versus time uh, axis, and we can see that it shows the similar kind of thing, over a half cycle of the line frequency, that is 0.01 if it is a 50 hertz cycle. So we can see that for the third case, that a ratio of 2, there is an area at the peak of the AC cycle where none of the modes are able to transfer the power, whereas for the other two, all the power transfer requirements are met. Now we do the same thing for the FEFB configuration, where all the power transfer limits are shown here by the different curves, and we plot the locus of operation for a ratio of 0.688 and 1.18. And we see that for the 1.18 case, there is a portion where none of the modes are able to transfer the required power. The ramifications are shown in the scapt versus time axis as well. And in this plane, we can see that there are two regions basically around the same voltage, that is near 1 of ratio NVAC by VDC, around that range. There are two regions here where none of the modes are able to transfer the power. Now we got to understand how these modulation boundaries are ramified in terms of power transfer and power quality. So a set of modulation modes can lead to a modulation scheme provided that the following conditions are satisfied. That is, the reference power is within the minimum and maximum power transfer of a certain mode when it is operating in it, and the maximum power transfer of a certain mode should be greater than equals to the minimum power transfer of the upcoming mode, and vice versa. So this ensures, the second condition ensures a seamless transition. Now looking at the power quality issues, if we do a simplification of the Fourier series for the power transfer, we get this equation. So what it means is that this is the peak power transfer here that is shown, and I mean, this is the reference peak power transfer, and this is the fundamental peak power transfer. So V1 and I1 is the these are the fundamental components. So this is the fundamental peak power transfer, and if this happens to be less than this, as we saw in some of the cases earlier where none of the modes were able to transfer power, so what happens there is, to hold this equation true, this harmonic content part needs to increase. So that's when PAC peak is less than P star peak, this condition, the harmonic content H increases, and this harmonic content, this guy, leads to the ISSTHD. And so if the harmonic content H is more, definitely ISSTHD will increase. So these are the ramifications in the power quality aspect in the AC side. So we would look at some of the simulation results where the power transfer P star is 35.1 kilowatt peak, which is kind of the optimum power transfer for such a submodule, and VDC is kept at 800. The half bridges capacitance are kept at 30 microfarad, and the Uh, FEFB configurations, filter capacitance is kept like a series combination of two 30 microfarad capacitances which gives 50 microfarad. The DC side filter capacitance is kept at 20 microfarad and the MFT's leakage inductance is 20 microhenry and the switching frequency is kept constant at 20 kilohertz. So when we do these three sets of simulations, that is for 0.688 ratio, 1.18 ratio and 2 ratio, we can see that for the first two cases we get very good power quality because here there is a smooth transition and here there is operation in only one mode, whereas for this case there is a situation where uh, during the peak power transfer period none of the modes are able to transfer the power and hence the IAC's THD shoots up. We do the same thing for the FEFB configuration where we show the two scenarios and the ISS TSD is quite good for the scenario where it operates only in mode 1 but the ISS TSD shoots up when the ratio is 1.18 where none of the modes are able to transfer the power at two regions as I showed you before. So now let's do a small comparison. So we can see the FEHB configuration has four less number of semiconductor devices. So it has total 3 degrees of control freedom compared to the 4 of FEFB. However, it has a more control flexibility as the constraints appear around voltage ratio of 2 compared to the voltage ratio of 1 for the FEFB configuration. So the control freedom required for the main three control objectives are being satisfied by the FEHB configuration, and thus we can conclude that it is a more suitable configuration because it not only provides some topological advantages but also better control flexibility, uh, better modulation flexibility, I would say. Now, we would show the experimental results only for the FEHB matrix-based dual active bridge. It is enough to show the modulation constraints for the FEHB matrix-based dual active bridge because we have seen that only the modulation modes 1 and 2 are able to constitute a reasonable mm, modulation scheme and all the other modes are useless because of a lack of seamless transition. So these are the experimental parameters and we do a scale down verification by scaling down both the voltage and current by a factor of 5 and thus we get this power transfer quantity here. And this is the first set of experimental results at 1.4 kilowatt with seamless transition between both modes 1 and 2 when the ratio is 0.688. So we can see a good input side or AC side THD of the current, and this is the pulse width and this is the phase shift and VPB as IP are the three waveforms for the MFTs voltages and currents. We can also see the VDC maintained at a certain or 160 volt DC and we zoom in the MFTs quantities that is the VP, VS and IP and we show it against a reference of VSC and VDC. So we show the similar things for operation at a ratio of 1.18 and we see that there's a operation only in mode 1 and superior current THD over here at the AC side. However, when the operation is at a voltage ratio of 2, we can see that none of the modes are able to transfer the power near the peak of the AC voltage or the AC cycle, leading to high total harmonic distortion for IAC, and it is beyond the grid code limits, which is unacceptable. So coming to the conclusion, a comprehensive study of the exhaustive set of modulation modes are provided for the two suitable MBDAB configurations and elaborate analysis of the modulation modes are presented for these topologies which reveals the modulation boundaries for each topology and The analysis shows that though the FEFB configuration has more degrees of control freedom and more modulation modes, it doesn't help in constituting a better modulation scheme. In fact, the FEHB configuration having four less semiconductor devices provides enough degrees of freedom, that is 3, which is required for the operation, and also provides better modulation flexibility compared to the front-end full bridge matrix based DAB counterpart. And thus FEHP MBDAB offers better topological as well as modulation related advantages. So at last we also show full scale simulation results and scale down experimental results which validate our proposed analysis. Thank you very much, and I'll be very thankful if you drop us an email if you're interested in our work, and thank you for your time.